So is equals to the integral of uh, um, all set of states, yeah, set of states, uh, and what is that integral? So we define the function in position space. So this is the way we define some wave function in position space. That is x, the bracket of x and t, uh, which is equals to the integral dx prime uh, of x, that is we are writing the unitary transformation t comma t prime, that we start from t prime to t, and x prime times x prime psi comma t prime. So what does this mean? The quantity here, this quantity, this is the matrix elements of U times the wave function of the particle at some earlier time t prime. So these are the matrix elements, matrix elements of U of t comma t prime. And what does this means? That is the matrix elements of U unitary operator multiplied by or times the wave function. This is the wave function. So this is the wave function in position space here. Wave function of the particle at some earlier time t prime. Yeah. So this is, and this is the wave function at some earlier time t prime. Yeah. And so it is the matrix elements of the unitary operator between x and x prime times the wave function at some earlier time. So so it's the it is the matrix elements of unitary operator ut t prime. Sorry. So this is t comma t prime, t comma t prime between x and x prime multiplied by or times the wave function at earlier time. Yeah. So इनफैक्ट इसको एक और भी नाम दिया जाता है इसको कहते हैं इट इज द कन्वोल्यूशन ऑफ द मैट्रिक्स एलिमेंट्स ऑफ द unitary time evolution operator. Yes. Convolution with what? Convolution is basically a type of a multiplication, but so here we have a convolution of the matrix elements of unitary time evolution operator with the wave function at some earlier time. Yeah, which is the earlier time t prime. Yeah. और if it is not an integral, अगर हम इंटीग्रल कन्वोल्यूशन की जगह अगर हम इंटीग्रल लेते हैं और सम लेते हैं, then उस सूरत में it would be just a multiplication, not a convolution. Yeah. So इस चीज को एक और भी नाम दिया जाता है and उसका नाम है also it is the convolution convolution of the matrix elements of the matrix elements of the unitary operator of the unitary operator with the wave function at some earlier time, at the earlier time. So what we want to do, we need to compute the matrix elements of a time evolution operator. Yeah. And we can also say in a very simple manner that matrix elements of the time evolution operator, uh, they imply that the matrix elements of this time evolution operator having some simple meaning. And what is that simple meaning? That is the state at some x prime in the ket is simply the state of the particle which is localized at a particular point in position space, and then the localized for that state x prime, so that the matrix elements of the time evolution operator then would define some quantum mechanical amplitude for a particle which starts at some point x prime and t prime to end up to a point x at some later time t. So uh, when we when we define this mathematical equation जो अभी हमने ऊपर लिखी है, so we would say that this would give you some sort of a quantum mechanical amplitude for a particle which starts at some initial time x prime and t prime, initial point x prime and some initial time t prime, and then it would end up to a point x at some later time t. And this quantity, this probability amplitude, is तरह से, this quantity has a very important bearing, and it has a is a name to it, and this is known as a propagator. So so one would say the quantum mechanical So quantum mechanical uh, amplitude amplitude for a particle which starts at a point x, at a point x prime and t prime, and uh, end up to a point to a point x at to a point x at some later time t. Yeah. और इसको क्या कहते हैं? This is this is an important quantity known as known as propagator. Yeah. So किसको कह रहे हैं हम? So this factor, that is the amplitude x comma t, x prime t prime. So this is the probability, and this is the quantum mechanical amplitude in going from some initial point x prime at some initial time t prime to end up to a point x at some later time t. And this is the amplitude to start at x prime, t prime, and end up at x t. Yeah. So propagator, we could think about this propagator, which is very important quantity, so that uh, once the propagator is known, unitary time evolution of an arbitrary quantum state can be obtained. So if you would like to know the unitary time evolution of some arbitrary state, what is important is to determine the quantum mechanical amplitude, which is in our case अभी हमने इसका नाम दिया propagator. So and then one would know how to calculate such a convolving state of affairs, and that is the propagator. And how do we solve it? We with the wave function of quantum mechanical state, we use a procedure जिसको हम इसमें इंटीग्रल से. Now this is a very simple sort of calculation where we start from one point, that is x prime t prime, and end up to a second point x and t, and we could have intermediate states as well. Yeah. But before discussing those intermediate state, we need to know one very special function which solves the equation of motion by performing an integral of a differential equation, and that function is known as a Green's function. So in particular, this propagator is a Green's function of the Schrödinger equation. So in physics, one knows the special function which which uh, which solves the equation of motion by, and how does it solve it? By performing an integral of a differential equation, forming an integral of a differential equation, and is called, इसको क्या कहते हैं? Is called a Green's function. This function जो basically solves some equation of motion by integrating a differential equation. This function is known as the Green's function. Green's function or functions. So in particular, this propagator, ये जो हमने बात की, propagator, that is जो अभी हमने ऊपर लिखा है, which basically propagates the system from some initial point t prime to some initial point x prime time t prime to some final point x and t, is basically the Green's function of the time dependent Schrödinger equation. This propagator, i.e. कौन सा वाला? x comma t, x prime t prime, and this is the, rather ये हटा दो, is the Green's function for the time dependent Schrödinger equation. So one should know that why this why this propagator, जो ये अभी हमने propagator लिखा है, इस propagator को Green's function क्यों कहा जाता है? So if you remember that the solution of Schrödinger equation in some special case where we start from some position x prime and some at some time t prime, that is we start from some initial point, that starting point is some delta function, yeah, rather than some imaginary initial state. So the starting point of that quantum system at some initial point x prime and at some initial time t prime is not some imaginary state, but it is some sort of a delta function, a spike rather. Yeah. So one could say that this imaginary initial state is some spike or some delta function at x prime and t prime, and that's why we call it as a Green's function. Yeah. So so if we solve Schrodinger equation, so uh, solving Schrodinger equation, कैसे we have Schrodinger equation iota h bar dava t and x comma t x prime t prime which is equals to minus h bar square upon 2m. Then we have this d square by dx square plus v uh, times x comma t x prime t prime. So this is x. Yeah. So we can solve this Schrodinger equation, but जैसे मैंने आपसे कहा कि earlier that before we solve this Schrodinger equation, हम इस propagator को थोड़ा expand करते हैं. That is, we try to find out whether there are some intermediate states as well, और उन intermediate states को इसके अंदर incorporate किया जा सकता है. What is the mechanism of incorporating those intermediate states? So, so, so before solving this Schrodinger equation, let us consider the propagator in depth. Propagator, propagator in some detail. And how do we solve this? So we call this x comma t x prime t prime is the amplitude, which is also the propagator. Remember, ये चीज फैक्टर एम्पलीट्यूड इसको प्रोपेगेटर भी कहते हैं, इज द एम्पलीट्यूड टू गो फ्रॉम x prime t prime to x and t. Yeah, so इसको एम्पलीट्यूड भी कहा जाता है, बट दिस can be rewritten in a in a in a way by considering some intermediate time slices as well. Yeah. So, but one can write this uh, in a way by considering some some intermediate times. Intermediate time uh, between t t and t prime. And how can we do that? We can write this amplitude for particle to go from some initial time x prime, some initial point x prime and time t prime to next point, let's say x1 and t1, and then to next point x2, t2, and so on, and then to go to from the second last point to the final point x and t. Yeah. So you can get the idea that these intermediate state can be can be written uh, such that as amplitude for the particle, the particle to go uh, from from x prime t prime to x1 and t1, and then to go from x1 t1 to final, let's say, position x t। या सो इस तरह से भी लिखा जा सकता है इस चीज को। और इस चीज को अगर मैथमेटिकली लिखा जाए, आई ई मैथमेटिकली, so we could write it x comma t, x prime t prime. This could be written as an integral dx, dx1. So we could think about x comma t, x1 comma t1, and then we could write x1 comma t1, and this is x prime and t prime. Yeah? So we could write it, and you see we have this in the middle, this quantity, and we have these two quantities at the ends, which basically describing you the fact that we are going from x prime t prime to x comma t, and we are summing over all possible paths. Yeah, so this integral represents summing over all possible paths. So this integral represents summing over all possible trajectories or paths, which is basically the significant feature of quantum mechanics. So this can be imagined as choosing some intermediate time t, or some, rather in this case, intermediate time t1 in between t prime and t, and the amplitude to go from x prime t prime to x and at t is the sum over all possible intermediate points, x1 where particle sits at time t1, and calculating amplitude to go from x prime t prime to x1 comma t1, and then from x1 t1 to go to x and t, and summing over all possible positions the particle happens to be at, and is the true and is true. And you can think about that if we have considered some intermediate position which is defined by x1 and t1, we can also think about more such intermediate position, and this is true for t1 as well. That is t1, x1 t1 can go to x2 t2, and then it is also true for t2 as well. That is x2 t2 can go from x3 t3, and this would also be true for t3, that is from x3 t3 we can go from x4 t4 and so on, up till we reach the final point which is x and t. So these are the intermediate state. This is just the sort of, हम इसको सोच सकते हैं कि it is just the result or consequence of just rewriting the basic feature of that unitary time evolution operator, namely that the unitary time evolution operator from starting from t prime to t is the product of two unitary operator जो हमने पहले शुरू में लिखा था। ये जो हम intermediate states को define कर रहे हैं, तो इसको हम इस पूरी चीज को ये भी कहा जा सकता है that this is basically the feature of the unitary time evolution operator itself. Yeah, that is the unitary time evolution operator which takes the state of which takes the quantum system from some initial time to some final time, can be written as the product of two time evolution operator, that is one going from t prime to t1 and the other going from t1 to t. Yeah, so this uh, can be rewritten rewritten as the basic feature of as the basic feature of the unitary time evolution operator, that is namely that the unitary uh, time time evolution operator from t prime to t is the product of two unitary operators, i.e. So u t comma t prime is equals to किसके बराबर होगा u of t comma t1 and with product with t1 comma t prime. Yeah, so we go from the initial time t prime to t1, and the other second unitary operator takes it from t1 to t. So now one can insert not just one intermediate states, intermediate point, but one can insert n intermediate points. And because of the composition of the property of the unitary time evolution operator, जो ऊपर इंटीग्रल इक्वेशन लिखी हुई है वो कैन सो सो फॉर मोर देन वन intermediate state uh, we could write x comma t, x prime comma t prime, and this could be written as d x1 to so on up till d xn minus 1. Yeah, so we could write it as x comma t or x1 comma t1, and we could go to the second one, which is uh, x1 comma t1, or this is x2 comma t2, and we go on to so on to xn minus 1 comma tn minus 1, and the starting point is x prime t prime. Yeah. So one needs to know what is the physical picture of this equation or this integral. What is the physical picture? So let's say we consider a pictorial representation that let the particle is at some final time t. Yeah, and from that final time to that final time t, it has come all the way from the initial time t to some time t1 to some time t2 up till tn minus 1, and then finally t. Yeah, so we could have the physical picture uh, can be obtained as as follows. So consider a pictorial representation that let the particle let the particle is at some final time t. Yeah, to take it to some final time t. And that physical picture कुछ इस तरह से बनाई जा सकती है. So let's say एंड सिंस हम बात कर रहे हैं ग्रीन्स फंक्शन, इस इंटीग्रल को सॉल्व करने के लिए ग्रीन्स फंक्शन, सो वी डिफाइन those those intermediate state and final state in the form of spikes or lines, as Green's function में होता है. Yeah, so we have this line which is t, and then we have another line which is t1, then we have another line t2, and we can go all the way to some a spike or line tn minus 1, yeah, and then some initial spike which is t prime. Yeah, so remember ये मैं spikes की सूरत में इसलिए बना रहा हूँ, लाइनों की सूरत में, because we are talking about Green's function. So at time t, the final time t, the position is x, yeah, and just before that the इसको सही कर लें. So just before this we have a point here, let's say ऐसे ही बना रहे हैं, pictorial representations हैं, and then it is it, and just before that maybe we are here, and then we could be somewhere here, and here we could make a gap here, so we go, yeah, and all the way we are here, and then we go to this point, we are here, so this is the x prime. Yeah, so this is x, then this point is x1, this point is x2, this point is xn minus 1, and this is x prime. So the time so we move from some initial time t prime at position x prime, and we go all the way to final point x at some later time t. This is some pictorial representation. So the time interval, yes. So one very important quantity is this time interval or this time interval, and this time interval is such that we calculate it as some initial intermediate time ti to some another intermediate time ti minus 1, which is delta t. Yeah, and this is somewhat very special, and it gives us the spacing between the two time points or two time slices. And the width of these time slices depends upon the number of stages or number of intermediate points. Yeah. So the time interval, the time interval is such that uh, ti minus ti minus 1 ये किसके बराबर है, डेल्टा टी के, टू बी टू बी वेरी स्मॉल, टू बी वेरी small, uh, and so what is delta t? This is some spacing. Delta t is spacing between between ti and ti minus 1 time points. Yeah, and this can be calculated by delta t, which is uh, t minus t prime divided by n. Yeah, so we have n such total number of intervals, and if we divide the total time between t prime and t by n, we get delta t. Yeah, so where n is the total number of intervals. Yeah, then the integral equation. You can view this you can view this integral equation as the amplitude from some initial position x prime at time t prime to some position x and at some later time t is just the amplitude to go between intermediate points. And this is important or relevant from the for the point here is that the integral at all intermediate points, that is from x prime to xn minus 1 to so on up till x2 to x1 to x, these basically these integrals are basically representing the quantum mechanical probability amplitude for those intermediate state. So in a limit where n tends to infinity, which means that time interval delta t between them goes to zero. That is, as n tends to infinity, delta t tends to zero. This is the sum over all possible paths that the particle can take, and only condition is here is that the particle start at some initial position x prime at some initial time t prime, and then it ends at a position x at time t. Yeah. So, but in between, it can follow all possible paths. Mathematically, this means that you can think about in a mathematical manner that when one integrates between x1, x2, so on up till xn minus 1, and one takes a limit where delta t is approaching to zero, essentially this is the sum over all possible paths, जो कि हमारी initial condition थी quantum mechanics में. And that जो कि difference है classical mechanics के एतबार से, because there we had a single unique trajectory. Here we have not a single unique trajectory, but we integrate over all possible trajectories that the particle takes between the initial that the particle can take between the initial and the final points. So this means that one expects that there should be a formula for this propagator, which can be written as an integral over all possible paths that the particle can take between those 2 points, that is the initial point x prime t prime to a final point x and t. वो फॉर्मूला अब हमें लिखना है इस फाइनल पिक्चर के लिए जो कि अभी हमने डिफाइन की है. सो